record it starting from now, so I can share it. Yes, so that's what algorithmic problem solving is. It's the intersection between algorithms, programming, and problem solving. I should say, when it comes to programming, the type of programming you will be doing in this course is not particular. I mean, I think the programming part is probably not the hardest part, but rather the problem solving and the algorithms part. So most programs that you will write are more in the order of like 50 to 100 lines of code. Very rarely there's a need to write significantly longer programs. But of course, you will be using sophisticated data structures and kind of programming constructs and so on. So I think it still will increase and develop your programming skills as well. Yes, so maybe I should say a few more, and that's I know that starting from last year, we now have a large number of Y-line students on this course, which have, you have significantly less prior courses in these topics. But I mean, our experience from last year was that it still worked out pretty good in the end. But you should be aware that you might need to spend some extra time on the algorithms part, which I think is the one that you have a bit less of. And then the programming, I think you have more than sufficient background there, but still it's good opportunity to improve your skills in all these areas. So why is this important? So actually this is a very old slide that I've been using for, I think, 8 years, 9 years, maybe now. And I think the really key thing here is that what we see today is that value in basically any sector of the industry is to a large extent created through software. That even if you're building cars, I mean, of course we have the examples of Tesla and Einride and others who basically are computers on wheels, and everything that's kind of providing, or not everything, but most of the things that providing value in those is somewhere through software. And we see the same thing happening with the telecom industry, or it has been happening for more than 10 years, of course, that the kind of moving away from ASICs or application-specific integrated circuits. You have very specialized hardware that was running the base stations and so on. Today, you basically have a normal, or well, you have like a Linux computer, and then you just have ordinary software running on this. And by changing the programming of these base station computers, you can change the functionality of the telecom network. And of course, we have the kind of digital native companies like Facebook and Spotify and Google and so on, which all are based on software. So the whole point here is that those that really can understand and take advantage of software technology, they are the ones that owns the future. I should probably say creates the future, because I think that's even more important here. It's about creating the future. And of course, not only the future, but also the present. And I also think it's really important to realize that if you want to have a job at these companies that you see at the bottom, like Spotify and Google and so on, I mean, the type of skills that they require are exactly the type of skills that we cover in this course. So I remember having a conversation with one of the Google recruiters a number of years back, and she was very frustrated when she was interviewing students, and they say that, oh, I'm really good at programming, and then she started to ask them about algorithms and data structures and so on, and they said that no, that's not important. I'm doing programming. And then they say, okay, well, thank you, because what they're really interested in is this kind of core. I mean, you want to have a formal understanding and be able to make sure that the solutions that you develop are actually working, and not only, well, I tested it on these 10 cases and it seemed to be working, now I'm fine. But actually, no, you have an algorithm which is guaranteed to be able to solve the interesting class of problems that you're addressing. And to give another anecdote related to this is actually one of the people who's working with Spotify and been working with Spotify for a long time, Jimmy Modell, who was one of the best competitive programmers when I was a kid, put it that way, when I was at university, like you are. And he said, and he was basically asked the questions, what's the difference between you and what you say, other programmers? And he says, I do it correctly the first time. And that might not sound that impressive, but as you've probably seen if you've taken any software engineering courses, that the cost of fixing problems basically grows exponentially between the time that you do them and the time that you find them. So the earlier you fix the problems, the cheaper it is. And of course, the cheapest problems are those that never even occur. So I really think this is another key skill that's being practiced and trained in this type of course, where, I mean, at least if you do this competitively, you actually get a penalty for every incorrect solution that you, or well, it's not a solution, every incorrect submission that you make. Luckily, we don't have such constraints here in this course, but which means that you should be quite convinced that whatever you're submitting is actually correct. And this being able to convince yourself and maybe also others about that this is actually a correct solution. That is another very important skill. And of course, there's also a lot of testing and analyzing going on in order to be able to actually achieve these things. So I really think this is a course which provides a lot of very practical and very valuable skills and tools to working in the software industry. Of course, I would also be very happy if anyone from Linköping University would also be doing well in these competitions, so the programming competitions. So the largest one is the ACM ICPC, the International Collegiate Programming Contest. So Linköping has been involved in these competitions since, well, actually since I was a student. I think I was one of the first to compete in this, and then we were going down to Lund and competing there. And then when I started as a PhD student, I started running contests here at Linköping. So I think the first one was 2000, fall of 2000. I think it was the first time I organized the competition. And we have also been in the world final once. I also think that was 2000. We were two teams competing back then, and of course there was the other team that made it to the world finals. But I think that's our only time in the world finals so far. And as you can see in these images, the countries the countries that are very much dominating these competitions is the Russians and the Chinese. But actually the Swedes are doing quite well. So especially KTH have had really good teams over the years. But I actually think, I mean, Umeå and Lund and Linköping, they have also had teams in the world finals over the years. And Sweden has also organized this competition once in 2009 in Stockholm. And I then started to be involved. So I've been what do you call it, director of analytics, so basically expert commentator to these competitions for a number of years, but now I'm retired. And of course it would be great that if Linköping would be again doing well in these competitions. And of course we organize these competitions, both the IMPA, the IDA Championship of Programming and Algorithms, which runs all the time. So you can actually make money from this course by participating in that competition. And we also organized the Nordic Collegiate Programming Contest, which is basically well, informal qualifier for the regional contest, which are then the qualifiers for the world finals. So that was very generally about the course. So now the interesting question. So what type of problems do we solve? And here, so I know it's a very small font, and I don't intend you to be able to read it as it is, but this is just an example of a particular problem. So this is actually the first problem on one of these contest sites, Universidad Valladolid, UVA. So this is the first problem there, and this gives you an understanding of what these problems look like. So they have this kind of general structure. So they have some kind of background. They have the problem itself. They describe the input and the output. And then very importantly, they have this sample input and sample output to give you some concrete examples of what the input and output looks like. So yeah, I already said that. So here I zoom in a bit. So if we now take this particular problem, the 3n+1 problem, and we zoom in here on the first two parts, the background and the problem. So the background, I mean, usually some text to kind of provide context for the problem, maybe describing in what situation it will be used and so on. In very many cases, it does not contain anything useful more than, well, sometimes we try to be funny or something, but in many cases, this does not contain any real information, but it can still provide a context to help you with the problem, of course. And then we have one very important, as you can imagine, part, which is actually describing the problem. So in this case, the problem is about a particular algorithm. And the algorithm is described in pseudocode. So it reads the input, it prints a number, or it prints the same number. And then if n equals 1, it will stop. If n is odd, then it assigns 3n+1 to n. Otherwise, it divides n by 2, and then it repeats. And that means that if we have a particular input, for example, 22, we will get a sequence of numbers printed, 22, 11, 34, 17, 52, and so on and so forth. So every time it's odd, we multiply by 3 and add by 1, for example, 11. Every time it's even, it will be divided by 2, like 22. So what you see is that you get a sequence of numbers. And when you reach 1, the algorithm terminates. And then we have in some sense the problem here, and that is, despite the simplicity of the algorithm, it is unknown whether the conjecture is true, which means that it terminates, because of course, as you can see, it sometimes reduces n and it sometimes increases n. So, I mean, there is nothing, it's not having a monotonic decreasing property, for example, or something like that you could use to prove that it actually terminates. So of course, this conjecture has not, as far as I know, still haven't been proved. But it has, of course, been verified for very large numbers. Here it says between 0 and 1 million. Of course, in reality, it's much larger. And then it says, given an input n, it's possible to determine a number of numbers printed before and including the one is printed. For a given n, this is called the cycle length of n. And in this particular case, for example, the cycle length of 22 is 16 because there's 16 numbers. And of course, the cycle length for 1 is 1. The cycle length for 2 is 2, and so on. So now we have a concept. Now it is defined this cycle length, and now it reaches what you're actually supposed to do, which is that for any two numbers, I and j, you are to determine the maximum cycle length of all numbers between and including both I and j. So given that you get the two numbers, you're supposed to find the maximum cycle length over all these numbers. So that part should be relatively straightforward. Now you have the details describing what the input and output actually looks like. So the input will be a series of pairs of integers, I and j, one pair per line. All integers will be less than 10,000 and greater than 0. So we know it's a positive integer less than 10,000. And now you should process all such pairs and output this maximum cycle length. And now, in some sense, maybe the even more important part, namely the output. And normally, you should really take the output literally, meaning that if it says you should have 3 spaces between the numbers, you should have 3 spaces between the numbers. Just to be on the safe side, often we'd often disregard white space, but there's no point in taking a risk. So it's very important to take this output literally. So it says that output for each pair of integers, I and j, you should output I and j and the maximum cycle length for integers between and including I and j. These 3 numbers should be separated by at least 1 space, with all 3 numbers on 1 line and with 1 line of output for each line of input. The integers I and j must appear in the output in the same order in which they appeared in the input and should be followed by the maximum cycle length on the same line. So for example, if you have 1 and 10, then the maximum cycle length is 20, and so on and so forth. So you see that they are repeating I and j, and then they're outputting the maximum cycle length. So this is a typical example of a problem which you will be able to, or that you will be solving through this course. So actually, I will leave the problem as it is, or I mean, you can always look at the slides so that you can cheat and look at the solution, but I think it's actually more interesting well, no, actually, I changed my mind. I will go through it. So this is an example of a problem which in some sense you can just solve by following the instructions. So basically what you need to do is to basically iterate through all your possible numbers and then compute the cycle length of each. And I mean, the cycle length of these small numbers, I mean, it's only 10,000. So it's actually possible to do this using a brute force approach. But of course, there is no point in, I mean, since the cycle length is unique for each integer, there is no point in computing it more than once. Here, a very useful technique is something called memoization, which is basically that you keep a table. So you see it as a cache or something like that. You basically have a table with an entry for each integer. And as soon as you have computed the cycle length for that integer, you add it to the table. And then if you need to know the cycle length of, say, 15, then you check in your table, have we already computed cycle length for 15 or not? If you have computed it, then just look up the table and return the value, then you're done. If you haven't computed it, then you compute it. So of course, this will greatly speed it up because every value will only be computed once. And as you saw in the example, by iterating through this sequence, you will quickly fill up this table. And I mean, in this case, since it was only up to 10,000, you could actually just store a table with the 10,000 values. And then you can solve this problem in constant time. You don't even need to do, well, actually, it depends on your table lookup, but if you have an array, then the lookup time is constant. If you use some kind of balanced tree or something like that, then of course it will be logarithmic time, but still it's very fast. However, this is an example of a problem who is deceptively simple, but there are several pitfalls that are very easy to get stuck in. And of course, it's that those are the things that you need to be really aware of. And here comes one of the hard and important parts of this type of problem solving, namely that you have to, if it doesn't say so in the problem statement, it probably is not true. So meaning that I mean, for example, in this case, it says nothing that the I and j are, I mean, that j is larger than I. So you cannot make any assumption in this case on the integers more than that there are between 0 and 10,000, which means that, for example, 112 is a perfect legal input. So this is the first gotchas. Usually that's easy to figure out. However, well, they can also be equal. I think that's less of a problem. However, this is the part that most people, I think, gets wrong with this problem. And it says that the order of I and j in output must be the same as the input. So you cannot just switch it. I mean, otherwise it just says that I is the min of I and j is the maximum of I and j, and then you're done. Or rather, you just, if I is greater than j, then swap. But that you cannot do. You need to remember the previous values. So this is another one of these examples, which might be much harder to realize. But I think the problem statement is very obvious on that. So that is a lesson learned here. If the problem statement says something, for example, it says here that the integers I and j must appear in the output in the same order in which they appeared in input. Every such statement is important and significant. So please you have to read these problem statements extremely carefully and make sure that every piece of information is used. And usually there's a lot of information in quite condensed text. So I guess that's the first challenge in this course, being able to read the problem statements. And of course, you will work up that skill. So what are then the course goals? So now we know a little bit about what algorithmic problem solving is. Why is it important? What are the type of problems that we are addressing? And now the question is, what are you intended to learn in this course? And the first course goal is to be able to analyze the efficiency of different approaches to solving a problem, to determine which approach will be reasonable, efficient in a given situation. So in many cases, there are very sophisticated and very fast solutions. However, it might not always be necessary. For example, I mean, in the previous problem, it was up to 10,000, which means that the problem is so small that you can actually use a brute force solution. However, if the problem would have been up to a billion, then of course you could not do it brute force. Then you would need to use memoization. And another consequence is that if you have up to a billion, you cannot use memoization either, or sorry, not memoization, table lookup, because usually you're not allowed to submit such large programs. So one key aspect here is the dimensions of the problem. So basically, how large problem instances can there be? And we can see that often there are several dimensions to a problem. I mean, in the previous problems, where basically the only relevant dimension was actually the maximum size of the integers. Maybe in some very rare cases, I mean, you could have relatively small numbers, say up to 10,000, but you have a billion input problems. Then, and if the total runtime is for the whole solving all of these, then you might have to have a faster solution. But other cases, it might be other dimensions. So if you have, for example, a two-dimensional array, then they have two dimensions, and so on and so forth. So this will be a very important part. So basically, you want to find the simplest but still efficient enough solution to the problem, and compare different problems in terms of their difficulty. So we have made some changes to this course based on the experience last year. I will come to them later, but it's as you probably can realize, it's clearly the case that all problems are not equally hard or equally easy, but rather they can be very different in difficulty. So being able to identify or rather order the problems by difficulty, so that you know that if you have limited time, because we will have something called problem-solving sessions. And these problem-solving sessions, there you will have a fixed amount of time to solve problems. And the goal is, of course, to solve as many problems as possible. So if you then start with the most difficult problem, you might not even be able to solve that problem. But if you start with the simplest problem, you probably will be able to solve that relatively quickly. And if you then find the second easiest problem and so on, then you probably should be able to solve 2, 3 problems. So being able to analyze the problems and identify the difficulty of a problem is another very important skill that you need to know. Yes. Then the second or third part is to use algorithm design techniques, such as greedy algorithms, dynamic programming, divide and conquer, combinatorial search, and so on, to construct algorithms to solve specific problems. Here it's about, so every problem in this course can be solved by developing and implementing an algorithm. In many cases, the algorithms are standard. So, you might use a max flow algorithm, or you use a minimum spanning tree algorithm, or something like that, sorting algorithm. And then, of course, you don't need to come up with these. It's sufficient to implement it. Sometimes you can just use a standard library, so there already exists an implementation for you. So you just need to call the appropriate implementation. But anyway, some problems you need to define or develop specialized solutions. In many cases, there is a need to tweak known methods. So it's not like you have to develop a completely new method, but you apply one. For example, probably one of the most common ones will be dynamic programming, where you solve different types of usually optimization problems by restating them as recursive solutions, and then you solve them backwards or use memorization to remember previous solutions, so that you only compute each sub-problem once, and thereby you can solve problems which otherwise would require basically brute force, that you try every possible combination. So being able to apply these different techniques and to develop your own solutions based on these techniques will be a key part of the course. I also mentioned this, that your solutions have to be correct and efficient, which means that if your solution works on everything but one tiny special case, I don't know, you forgot that the input could be empty, everything else is correct, you still don't have a solution. You have to solve every case, otherwise you don't pass the problem. So, and this is usually the hardest part. Often it's might be kind of straightforward to understand roughly what you're supposed to do and come up with, say, defining the right algorithm. But then to get all the special cases, get the corner cases, get the extreme cases, and so on right, that can in many cases be tricky. And since the point here is also to the furthest extent possible correspond to how things are done in real life, it means that you will not get all the input, or all the answers, but rather you will get limited feedback from the system, and basically you will know roughly what type of problem it is. For example, that you got the wrong answer, your program crashed, or your program was too slow. But apart from that, you will not get any more detailed information, which means that you will need to learn how to test and debug these programs and come up with the correct solutions. Remember the anecdote of Jimmy Model, do it correct the first time and you will save a lot of time. And this actually, well, the first part is probably not that key that anymore, but correctly implement a given specification of algorithm and data structure, well, it's also quickly in the sense that, I mean, in these problem-solving sessions, you will have limited amounts of time. So it means that you need to be able to do it relatively quickly. But more importantly, you have to correctly implement them. So it's not enough to kind of have the right algorithms, know what it's about, but you actually have to implement it so that it works for real and that it's fast enough. And my experience working with this for well, close to 25 years now, actually, it might be even more depending on how you count, is that this is actually the hardest part. That, or the last two ones, I should say, are the hardest parts. That many people are able to realize, oh yeah, this is a max flow problem, for example. And yes, I do know about these max flow solutions. So, I mean, you can look up the algorithm. So now you have the algorithm, you know, yeah, what to do. But then, and then you probably can implement it, having something that maybe works on the input test cases, but then you get the wrong answer or something like that. And then actually finding why doesn't it work, and ironing out all the small details that may be missing. So don't be surprised if those are the hardest part. But I think in the end, those are in some sense the most important part, because it doesn't matter if you have the right idea. If you're not able to implement and execute on that idea, well, then you will not get the real value out of it. So this execution phase and implementation phase is actually key. So these are the course goals. Oh, there's one more, and that is about communication and cooperation. So actually, this has due to what should we say, natural causes or understandable causes, not been that pronounced the last year. But anyway, I think that all real problem solving is done in teams of some sort. And in order to solve interesting and complex problems, you need to cooperate with others. So therefore, communication cooperation is actually very crucial to being successful in algorithmic problem solving. Therefore, we have these group problem solving sessions. So 1/3 of the problem solving sessions are done in groups, or normally done in groups. We didn't do it the last 2 years, but hopefully we can do it this year. And then you need to solve problems together, and then you need to either divide, so how to split up the problems among yourselves, or I mean, I think for testing and debugging, working together is great, because if you can describe for someone else what the problem is, and then try to explain what your solution is or your program is supposed to do, then first of all, you need to think it through, and that's a great way of convincing yourself that you have the right thinking. But it's also the case that this is a way of for the others to provide feedback that, wait a minute, that does not work out, or oh, okay, but then you forgot this part, or you switch these indices around or something like that. And then it's a great way of improving the quality of your problem solving. So this is another very important part. Okay, so now we come to the actual examination. So there are two parts of the examination. One is the lab exercises. So here there are two parts. The first one is basically implementing. I mean, you know exactly what you're supposed to implement. I mean, I mentioned max flow several times. So max flow is one. You have string matching and computational geometry and a bunch of other things. So basically standard algorithms that are very useful. That's one part that you get points for. And then the second point is using these in real problem solving sessions. So there will be 6 problem solving sessions throughout the semester. And you need to participate in at least 3 of these, 2 individual and 1 group. So you can participate in more, and then we count the best 2 of the individual and the best 1 of the group. So it's beneficial to participate in multiple of these to improve your score there. And then that's the first part. Then we have the exercises. That's the second part. So this is the part which we have hopefully significantly reduced or improved and reduced the amount of work needed. So one of the criticism of the course previously, especially last year, was that to get the passing grade was, I mean, reasonable, but to get the higher grades, there were a lot of, you had to spend significant much more time on this course. So therefore we have restructured so that you need to solve fewer exercises and still get higher grades. And basically it's about solving harder problems. So you don't need to solve more problems, but you need to solve harder problems, as I will show on the next slide. So I got a question about, are you allowed to discuss labs or exercises with other, or is it strictly individual? So the key part here is that you have to individually implement and, more importantly, understand the solution. So you're more than welcome to discuss the kind of general idea and the approaches and so on, but you should do your own implementation, and you should be able to explain how your solution works. Because if we are uncertain whether you actually did it yourself or if you collaborated too much or too extensively, or basically took someone else's solution, one step will be to ask you to explain how it works and why it works and so on. So of course that is the most important. It's recommended that you try to solve as much as possible on your own, but you are allowed to discuss the general problems. And I should also say that the labs are even more, I mean, there you know what the problem is. So there a bit more collaborations is acceptable. Okay, so then we have the new grading. So basically, as I said, there are 13 exercises, so 13 weekly exercises. Each weekly exercise have 4 problems in them, and they are of 3 different difficulties, A, B, and C, where A are the simplest problems and C are the hardest problems. And as I said, to pass the course, you need to solve at least 13 problems, 1 from each problem set. So you have to solve 1 problem from every problem set. So that's the first condition. You have to solve at least 1 problem from each of the 13 problem sets. If you do that, then you get a passing grade. If you also want a higher grade, then you need to solve more problems. So to get a B, you have to solve at least 7 more problems and 7 more B problems. Of course, a C, I mean, if you solve, say, 5 B problems and 2 C problems, that's also fine. And then to get the grade 5, you need to solve at least 7 B problems and at least 6 C problems. So now you have to solve at least 26 problems. So basically, if you solve 2 problems every week, 1 A and 1 B or C, then you will get the highest grade. And once a week, we will go through the weekly exercises. And since we then will describe the solutions to the problems, it means that you will get 1 point for each solved problem before the deadline and 0.5 problems after we have explained how it works. So, which means that, for example, if you're, well, in the worst case, so to speak, you never solve anything on time, you solve everything after time, then you will need to solve 26 A problems or harder. You have to solve 26 problems to get the 13 points. But if you solve 1 problem every week, then you will pass this part. If you solve 2, where the 2 or the other one is a B or C, then you will get at least 4 and maybe 5. So I think this should be much more reasonable compared to last year, where you had to solve basically at least 3 problems, I think, every week to get the highest grade. And of course, we very much welcome feedback. So if you have comments on how. So the question is, when is the deadline for each week and when does the first week start? So the first period, most seminars are on Fridays. I think it's at 10. So the first exercise is due next week. So you have a little bit more than 1 week to solve the first set of exercises. So the deadline is right before the seminar. So if the seminar is at 10, then the deadline is at 10. So as long as you have solved it before the seminar, it counts. And then I think in the second period, I believe it's, maybe it was Fridays there as well, but it was at 1 instead of 10. Oh, well, I don't remember, but you can see it says clearly on the exercises when the deadline is. There's a question about, will B and C problems also be discussed? Yes, we will go through all the problems. All 4 problems will be discussed. Do you need to participate in the seminars to get the points? No. Participation in seminars is voluntary. So actually, the only thing you need to participate in are the problem-solving sessions. Everything else can be done completely asynchronous and on your own. So it's only the problem-solving sessions where you need to participate. And we will have to see how those problem-solving sessions will take place. I mean, since it is examination, we would prefer to do it in the computer rooms. But as you probably can understand, it's dependent on the pandemic situation. So schedule, yeah. So I realized that I think I might not necessarily, yeah. So I think I've updated the schedule, but I do think there might be some changes that I forgot to upgrade. I realize now that I see it. So don't take this schedule too literally. This schedule is on the web page. So the web pages are correct. And they're all the correct dates for all the exercises and labs and seminars and so on are already. But the general structure is that there is a seminar. So basically, of course, we will not do any lectures because I've just recorded the lectures. So there will be recorded lectures giving a very high level introduction to the area. So for example, data structures. So here I think is the first error. the deadline for the first exercise is not on Friday, but the Friday after, I hope. But anyway, that the structure is that we go through the topic, for example, data structures, and then the week after that, the problems that you will be working on will be on data structures. The seminar the week after, we will go through these data structures problems, and then starts with the next area. And then roughly after half the period, there is the first individual problem-solving session. So this will be based on the first lab, and then roughly second half of the period will be working on the second lab. And these problem-solving sessions, the problems selected will be such that you benefit from having implemented the labs, and you're allowed to reuse the code that you have done in the labs. So doing the labs will help you in the problem-solving sessions. And therefore, the deadline for handing in the labs are the same, but there are no penalty if you solve them later. So that means that the first problem-solving session in February will be working on problems from lab 1. And then after 2 individual problem-solving sessions, there is a group problem-solving session on the first 2 labs. And then we repeat that for the second period. So there were 2 individuals based on lab 3 and lab 4. And then there is a group problem-solving session on labs 3 and 4. So that's the general schedule. There is a question about how do you assign the groups. So previously we have done that. So basically you form your own groups. Sometimes there are people that do not have any groups, and then we help with doing that assignment. But to the extent possible, we want it to be voluntary. Okay, I see that it's a little bit after 9, so I will make a break now, and we will resume again at 9:15, so in slightly less than 10 minutes. Okay, welcome back. Sorry for the slight delay. I had to update the schedule. Apparently, it was quite inconsistent. So now I've updated the slides here. So tomorrow and on Thursday, we will have a practical introduction to how to solve algorithmic problems. The first one tomorrow will be more, we say, theoretical, and then on Thursday we will implement the same problems, so that will be practical. So hopefully then you should have an understanding of what the problems are, and then be able to implement them. And then next Friday on the 28th is the first deadline. And then I've updated all the other deadlines here as well, so now it's correct. So I got some question, should every part of a lab be solved? So I mean, each lab that gives you credits will be a separate submission. So I mean, it will be cleared. I mean, if you have submitted it, it got accept on that column in the kind of result table, then you're done with that part. So you don't need to solve everything, but you can solve a subset of it. Regarding programming languages, so the purpose of this course is not a particular programming language, but rather to solve algorithmic problems. CutThis is CutThis is the automatic correction tool that we use, automatic judge that we use. It has a wide variety of languages that it accepts. You're welcome to use your favorite language. Most people use C++, Python, or I think Java has declined a bit, but one of these 3 languages. I do actually think I have a slide on this later, but since I already started to talk about it, I can say it again, that every problem is guaranteed to be solvable in C++ and Java. So C++ and Java, you can solve every problem with. Python, and I mean, all the other languages, there are no such guarantees, which means that some languages might be too slow to solve certain problems. For example, Python can sometimes be slow, but in many cases it will be fast enough. So probably you can solve most problems using Python, but probably not, well, I don't know, but maybe not every problem can be solved in Python. So if you're using C++ or Java, at least you're guaranteed to be able to solve it. And if you use other languages, in many cases you can solve it, but it's not guaranteed. How many points are needed for lab 1? See the course webpage for that part. I don't remember it in my head. It's on the examination page. The lab session on Thursday, is that on lab 1 or something else? So the lab session on Thursday is on this introductory problem solving. So we're basically doing a problem solving session for practice. And the problems that we will be using are the same that you will be discussing tomorrow. So as I said, that's the practical part of this introductory problem solving session. Can all problem input be assumed to be valid in accordance with the problem description? Yes. There are known cases, for example, the World Finals of 2020, when 2000, sorry, where the judges refused to accept that their input data was incorrect, but it was. But of course, these problems we have been using many times, so they should not have any issues. So yes, you can make that assumption. Is the seminar tomorrow a pre-recorded lecture? No, yeah, no. So maybe I should say this. Let's see. I go back. So since you are now many students, we have about 90 students registered for the course. We now have two course assistants, Herman Appelgren, who was the course assistant last year as well, and Leif Eriksson, who is a PhD student in the theoretical computer science group and who took the course a number of years back with very good results. So they are the two course assistants. And since we have two, we have therefore decided that we will provide both on-campus and remote opportunities when it comes to the at least to the labs and to the introductory seminar as well. So tomorrow there will be you can either come to campus and participate in the seminar in the lecture rooms in the schedule, or you can participate remotely. And the same what goes for the labs. So there will be at least one course assistant in the lab rooms as per the schedule. And there will also be one lab assistant who is available for remote questions. And they will provide the information about how that works, how you kind of interact with them for that. So there will be a hybrid mode. So based on how things go tomorrow, we will make a decision on how to proceed with the remaining of the seminars. I'm not too fond of duplication, so we might select one or the other for the seminar. So I should say that seminar part is where we discuss the solutions to the problems. These are for natural reasons not recorded, nor are any slides shared. But the kind of lecture part is pre-recorded. And I should also say, when it comes to the lecture part, that the course book is very, very good. So, I mean, it's very practical and hands-on, and basically it has all the algorithms that you need for this course and many more. So that should be adequate to address those things. Can you change from time to time if you do it remotely? Yes, we will not keep track. I mean, as long as we suddenly don't have like 90 people trying to cram into a small room, well, I guess if there's no one there, that's probably unlikely, but yes, you are allowed to change. But we hope that it will be reasonably stable so that we can adjust accordingly. Yes, okay. I think I answered all the questions. Very good questions. Thank you for asking them. Yes, so now we come to so that was in some sense overview of the course. And now we have this introduction to solving algorithmic problems. So in some sense, the process for solving problems is very easy. Of course, it's easier to say than to do. So the first part is estimating difficulty. So here you have a number of things you could look at. You could look, for example, at theory. I mean, is the problem very small? As I said, if it's a very small problem, basically any solution might work. If it's very large problem, so the input sizes are extremely large, then it will be harder. Maybe you can see this is a known algorithm, then probably it's easier. Sometimes, I should probably say that in this course, not that much, but sometimes there are known theorems. So basically you can analytically either solve the whole problem, which is unlikely, but more importantly, you might be able to reformulate the problem so that it becomes easier. Actually, we did have one such problems that we removed because it was kind of not that interesting. And then the second part is the coding, and this is basically, I mean, will it be a large program, which is rare? Will there be many cases? So I mean, some problems are easy, but the kind of you have to do a lot of different things depending on what happens. So there's a lot of choices that might make things harder. There might be complicated data structures. So I think, I mean, I don't know if it's complicated, but I mean, a suffix tree or something like that is a bit more complicated compared to just using an array, for example. So sometimes that can make things harder. So those are kind of two general things. And then the more individual part, which is, have you seen this problem before? Maybe I've already solved it before, or a very similar problem, then it should be easy. Maybe you have code in your code library. And of course, the purpose of the labs is to help you build up a code library that you can use so that you can solve problems faster. So that's the first part. So basically, the first part is, should I try to solve this problem at all, or should I take another problem? And if you are in a contest situation or in a problem solving session situation, you should of course try to solve the easiest problem first. So your quest is to find the easiest problem first. Okay, now you have selected a problem. Great. Now you need to understand it. So what is being asked for? This may sound like a trivial question, but in some cases it's not. And here you have things like, what is given? What do they say in the problem statement? How large instances can there be? Again, look at these bounds. How large can the numbers be? That will tell you a lot about what type of solution it is and what type of solutions are required. Maybe you can draw a diagram to help you understand the problem. So maybe you need to visualize how it works. Can you explain the problem in your own words? So I said previously that if you're working in teams, if you have a problem which you're not sure about, if you understand it, try to explain it to someone else. If you manage to explain it to someone else that they understand it, probably you understood it as well. Can you come up with good examples to test your understanding? So for example, that, if my understanding is correct, if I give it this input, this will be the output. And then you can go through and say, yes, that seems to be correct. So these are all strategies to help you understand what you're asked to do. And then now you understand the problem. And now you need to find what is the right algorithm to use, algorithmic approach to use to this problem. And here, I mean, in some sense, my suggestion here is to try the simplest solution first. If you can use brute force, use brute force. There's absolutely nothing wrong with brute force if you can use it. So, of course, what you want to do is to select the algorithmic solution, which is the simplest for you to realize, fastest to implement, and to get correct on the particular problem. Sometimes it is just try every possible combination. That might be very easy. Unfortunately, or however, that's very unlikely. Usually the second simplest solution is greedy approaches. So basically you can just do a local choice, local optimal choice, and it will lead to globally optimal solutions. Concrete examples here are, for example, coin change in what you say reasonable coin structures, such as, for example, the Swedish coin structure. Then you can always use a greedy approach if you want to return the fewest number of coins to give change. Of course, no one these days knows what coin change is, but that is not part of the problem. Then we have dynamic programming. As I said, if you have an optimization problem, for example, you want to find classical examples here are knapsack problems. So you have a knapsack or rucksack with a maximum weight capacity, and you have a bunch of things that you would like to add to your knapsack. Each item has a value and a weight. And now the question is, what subset of items should I add to my knapsack so that it's within the weight constraints of the rucksack or knapsack and has the maximum value? That's one example, and that's solved by the dynamic programming. So very many problems in this course can be solved by dynamic programming or have algorithms that are based on dynamic programming. And then there are general techniques such as search. So basically search can solve every problem. Well, I would argue that search can solve every problem there is. And I mean, search is basically the foundation for optimization, which is, for example, the foundation for machine learning, to take one example. So machine learning is all about search. You're searching in the parameter space, and then you're using the gradient as the heuristic, and you use that heuristic to guide your search so that you can quicker find a reasonable assignment of values to your parameters and so on. So search is extremely general, and I would argue that brute force is a form of search where you basically systematically try every possible combination. So it's what, it's basically exhaustive search. So you try every possible combination. But of course, you would like to check as few solutions as possible. So often you use the form of heuristic search, which means that you have some heuristic or rule of thumb or guideline to guide you in your search. And I said, I gave one example of this stochastic gradient descent, which is an example of heuristic search, where you compute the gradient and you take a step in that gradient's direction, and then that directs your search. But of course, we are not working with numerical algorithms that much in this course, so we will use more discrete versions, like branch and bound or A star or something like that. And then can you solve the problem using a known algorithm in your code library? Of course, if you already have a solution, great for you. Can you modify an existing algorithm? Maybe instead of finding, say, the shortest path, you know how to find the longest path. Or instead of having additive weights, you have multiplicative weights. So you have to take the logarithm instead, so that you change multiplications to addition, and so on. And sometimes it's that you have to modify the problem to suit an existing algorithm. And here, for example, we have many matching problems. So, for example, you can rewrite a lot of problem to maximum flow. So basically, rewriting it a maximum flow problem, and then you solve it using your standard maximum flow algorithm, and then gives you the maximum bipartite matching or something like that. And in the worst case, you have to come up with your own algorithm, which, of course, probably is the most time-consuming part, but or not part, but the approach. So that should preferably probably be your last resort. But the overall guidance here is to use the simplest approach that you will be able to solve the fastest. And now you have the right algorithmic approach. Now you just have to solve it, which of course, again, is easier said than done. So this is a very general approach to algorithmic problem solving, but I think it's very applicable. So now an important word from our sponsors, I was supposed to say, or almost going to say, and the reason is that this table is taken from the course book, and it's extremely useful in determining what type of solution are required to solve a particular problem. So you can assume that the normal time limit for a program is a few seconds. And of course, I mean, you can consider that there will be potentially thousands of people solving the same problem over and over a time. So if you're owning the hosting infrastructure for this, doing the automatic testing, you don't want to spend too much time, and for many other reasons. So basically, you can assume that the normal time limit for a program is a few seconds. More operationally, you can assume that your program can do about 100 million operations within this time limit. So normally, if your program are within this 100 million operations, you will manage. So this is an extremely useful heuristic. And now the interesting question becomes, okay, assuming that we have 100 million operations, what can we do? And that is what this table tells you. So for example, if we have n faculty, so basically we have to do every possible permutation. So for example, we have brute force solutions to n queens problem or something like that. Then we have n faculty number of solutions, which is actually the same as n to the power of 6. So even though the first one is exponential, actually it's n to the power n approximately, it's with these small numbers up to 100 million operations, that is not more than n to the power 6. So it means that if you have 6 nested loops, it is as bad as trying every possible permutation. And then you can only do problems of like size 10, 11. If we have 2 to the power n. We have an exponential algorithm that also have a quadratic term. For example, we're doing dynamic programming over travel and salesman's problem. So basically we have n to the power 2 combinations, and we have we have exponential number of possible routes. Then we can do 15 to 18. If we use bit mask techniques for DP, which is extremely useful. So basically, instead of having a set, instead of having sets of elements, you can basically encode a set as an integer, where each bit in the integer represents a particular element in that set. And then we can basically just do enumeration. So 0 is the empty set, 16 is the set of the 15 is the set of the first 4 elements, and so on. So then we can much more efficiently represent sets, and we also represent other things. And then we can now reach about 18 to 22. So now we're still at the exponential. And now we're getting into the polynomial range, namely n to the power 4, for example. So you have dynamic programming solutions with 3 dimensions and loop in the center. So basically you have to do 4 nested loops. Then you can do 100 cubic solutions. Now we're at 450, for example, Floyd-Warshall's all pair shortest path. 2k, now we're down to n to the power 2 log n. So for example, we have 2 nested loops plus a tree search. So you might have a balanced tree or something like that, or you're doing a lookup in a map. So you have 2 nested loops and a lookup in a map. Then you get n squared log n, and now we can do about 2,000. N squared, we can do 10,000, and now we have kind of simpler sorting algorithms, selecting and sorting algorithms. And now we finally get into the interesting cases, namely 1,000,000. Then you need an n log n. So here we have basically most divide and conquer approaches, like merge sort and binary search and so on. We also find most computational geometry methods. So most of those are also sort and then process the elements. You have n log n plus n. And then we can do about 1,000,000. And finally, if we're going to have up to 100 million, then we need to come down to linear, logarithmic, or even constant time complexity. And here we have simple things like just doing simulations or finding the average and so on that you can do in linear time. Of course, since we're working only with 100 million operations, the constants in your complexity analysis might play a role. So as I'm sure you're aware, the Ordo notation basically removes all the constants. So it's only the kind of what is the most dominating factor in your polynomial description of how many operations are required to solve an instance of a problem. But this should give you a very good indication of what type of solution is required. So have this in mind. Very useful. So now I basically have a very brief tour of the different problems or the different kind of content of this course, and in some sense these kind of approaches. Simulation, I said, basically you just do what's stated in the problem, and the classical example is, for example, a robot. So the robot has some starting location, it's given a program, and you're supposed to figure out where will it end up, for example, or this and 3n+1 problems, more or less also simulation ad hoc. Greedy solution, I already mentioned. We have like minimum spanning trees, coin change, so that you can make a locally optimal decision, and that will lead to a globally optimal decision. So there's no need to backtrack or reconsider any previous decisions. Divide and conquer, you take a large problem, split it up in smaller parts, and solve these smaller parts individually. and then you put the pieces back together to get the overall solution. Here, classic examples are merge sort and quick sort, but actually a large number of algorithms are divide and conquer. Divide and conquer, dynamic programming, find a recursive solution and compute it backwards. So usually the thing here is to that you're recomputing the same subproblem multiple times, and you avoid that by only doing it once, and then you can reach sufficient efficiency. Finding the shortest path in a graph or coin change in all currencies are examples of dynamic programming. I also gave this example of the knapsack problem. Search, I already said, is basically you systematically try different partial solutions to a problem, and then as quickly as possible you try to determine, can this lead to a solution or not. Otherwise you have to go all the way to the leaves in your search tree and then check if this is a solution. If it's a solution, you're done. Otherwise you need to continue the search. And here I would say that depth first search is extremely useful, basically just going as deep as possible into the tree before you reconsider. Binary search, extremely useful, basically dividing the search space in two and going down and then having a choice for which direction to go in. Heuristic search and so on. So very, very useful techniques. So just to give an example, when it comes to complete search, so if you have a small problem, you can basically, then you can try all possible candidates. That is then a complete search. And of course, to determine if this is feasible, you need to estimate the number of calculations that you need to do. And then there are two general ways of implementing complete search. Either you do iterative complete search, basically using nested loops to generate every possible complete solutions, and then you filter out the valid ones, and then you get a set of solutions, and sometimes you need to find one solution, sometimes you need to find the best solution, so therefore you might need to keep one or more of these. And here there are some very nifty operations or standard library tools, for example, next permutation in C++. So this will allow you to, in a single for loop, iterate over all permutations of a sequence. So you basically just iterate over next permutation. So very, very efficient and simple implementation. We can iterate over all subsets using the bitsec technique I described earlier. So basically you consider if you have n elements in your set, then you use an n-bit number, and each bit in your number represents one element. If it's 1, then it's included in the set. If it's 0, it's not included in the set. And now you can iterate between 0 and 2 to the power of n minus 1. And then you will be able to, again, with a single loop, represent all subsets. Extremely useful. The second type of complete search is recursive complete search, in which you extend a partial solution with one more element until either it's complete and a valid solution is found. I guess you can also have that it's not possible to extend it to a complete solution, and then you can also end. And often this is called recursive backtracking, because when you cannot extend your solution anymore, or your partial solution anymore, or you reached the end, then you backtrack, which means that you jump up and you restart going down or right usually. And here a very efficient technique is called pruning, which will allow you to significantly improve the efficiency by removing partial solutions that cannot lead to a solution. It could also be, for example, if you're finding, say, the fastest route, then if you already spend more time than the best solution found so far, there is no point in continuing because it's a monotonically increasing length. So therefore, you can prune and then remove this partial solution and backtrack and continue. So this is also extremely useful and extremely general techniques. And one concrete example, assume that we have, say, a diaphantic equation such as this, where you need to find which 3 integers, x, y, and z, which satisfy the three following relations. So in this case, you can basically write a program that will try every value of x, y, and z, or z. Well, I'm changing between English and British. Anyway, and then you basically just compute. Of course, in this particular case, you can do a lot more efficient. For example, there is no point in having 3 nested loops, for the simple reason that if you have x plus y plus z equals a, where a is a constant, of course, if you know x and y, then you know what z has to be. You also have this constraint that x times y times z should be b, which of course, since you have multiplication, it probably will greatly reduce the size of the others. So for example, the first equation, so that if you have x and y, you will be able to compute z. So that means that you can only need 2 nested loops to do this. And then since you have x times y times z equals b, it means that if you know what x is, if you assume that z is 1, you know the maximum size of y. So it means that you can greatly reduce the end, or in some sense, how many different values of y that you need to test, so that you can greatly, again, reduce the search space. So on and so forth. So that even though it's a very straightforward problem, you can often do a number of things to speed things up. But this is an example of, I guess, would be iterative complete search. Divide and conquer. So again, this is a very powerful technique where you basically take a large problem, break it down into 2 smaller parts, and you solve the 2 smaller parts individually, usually recursively applying divide and conquer. And then when you have broken down the problem to the smallest pieces, then you put the solution back up. And here, binary search is, as I said, extremely versatile and useful technique. So for example, if you have sorted range, of course, the classical example is the telephone catalog that doesn't exist anymore. But when I was a kid, we had actually a physical book containing all the phone numbers of people sorted by their names. And if you want to find a particular person in this catalog, you basically start in the middle. So if you're looking for, I don't know, Gustafsson or something, then you look in the middle of the catalog and you see, is G to the left or to the right? And now by having one lookup, you have discarded half the book. And then again, it's probably to the left. So then you take the middle of the leftmost part of your telephone catalog. Again, you look in the middle and then you see, is G to the left or to the right? I have no idea, maybe it's to the right. And now you have in two comparisons discarded 3/4 of all the possible pages in the book. So you see, it's a logarithmic solution. So it's very, very, very useful. You can also use it to find parameters of a convex function, so that if you know it's convex, then you know which direction to move. You can find a minimum maximum value of function and so on and so forth. And you can either implement it yourself, or you can use built-in functions like lower bound and upper bound. Sometimes you need to iterate until you find a small enough difference. You can also compute the maximum number of tries that you need and just do that many iterations and then be done with it. And here, the classical example is quicksort. So quicksort is actually a randomized sorting algorithm based on divide and conquer. So you pick some element, which is called a pivot element, and then you partition your set into 3 sets. The elements that are lower, the elements that are equal, and the elements that are greater. All the elements that are equal, you're basically done with. And now you apply this recursively to the lower elements and to the smaller and the larger elements. And then you do that recursively. And in each step, you will kind of sort these subsets. And at the end, you just put these 3 sets together, and then you will have your final solution. So for example, if we have, in this case, we have 7, 2, 9, 4, 3, 7, 6, 1. We randomly select 6 as your pivot element. That means that all the smaller elements go to the left, 2, 4, 3, 1. And then you do that recursively. So in this case, we we selected 2. Then we just sort this, and then we have the elements to the right, 7, 9, 7, and then we sort them again, and then we just append these different parts together, and then we get 1, 2, 3, 4, 6, 7, 7, 9, and then we're done. So this is then an example of divide and conquer. Greedy algorithms, I've said many times now that we make this locally optimal choice, and that should lead to a global optimal solution. And the requirement for doing that is that the optimal solution, or rather it has the optimal substructures property, which means that an optimal solutions contains the optimal solutions to every subproblem. So if we have a smaller problem, the optimal solution will be a subset of the larger problem. And the second one is it has the greedy choice property, which means that if we extend a partial solution, so basically we have a partial optimal solution, and then we add the next element. If we can do that so that the added element is also optimal, then of course, then by induction, we get that the end result is also optimal. And the example here is coin change. So I mean, if you have 10, 5, and 1, and now you're going to return, I don't know, 22, then you just take the largest, and then you return as many of the largest numbers as possible, 2 10s. You can have no 5 and 2 1s. So 22 will give you 2 10s and 2 1s, and that is the optimal solution. Sometimes greedy algorithms can be useful for heuristics. So for example, if you're using a branch and bound search algorithm, then you need to have a good lower bound or a good upper bound. And then you can use greedy because they will find a solution, but might not be the optimal solution. And if you're interested in combinatorics, so then there are specialized matroids called greedoids, which then characterize classes of problems with greedy solutions. So you can also have a more kind of combinatorial or algebraic approach to the whole thing. And one of the most well-known examples of a greedy solution is Kruskal's minimum spanning tree algorithm. So in the minimum spanning tree problem, we have a graph, an undirected weighted graph, and we want to find a tree that covers all the nodes, which means that we want to find a tree, a subset of the edges that connects all the nodes, but there are no cycles. So what we do then is that we sort the edges by increasing edge weight. And then we just select the cheapest edge of this, and we add it to the tree unless it forms a cycle. So of course, the first edge we will always add. We can add the second edge as well, because you cannot get now you cannot get a cycle with 2 edges. And now we get to the third edge between E and G. That we cannot add because that would form a cycle between D, E, G. So therefore, we do not add that edge. And then we take the next one, C, D. Yes, we can add that. G, H. Yes, we can add that. C, F. Yes, we can add that. B, C. Yes, we can add that as well. B, E. No, it forms a loop. D, C, B, E, and so on. So then we can just go through these edges in order. And when we do that, now we will get the tree containing the red edges. And this is the minimum spanning tree of this graph. And that we can then do using a greedy approach as one example. And finally here for today, we have dynamic programming. So here you basically, so I mean, my standard approach here is that write up a recursive definition. So basically you define the solution by a recursive definition, and then you either use memorization to store the previous solutions, or you compute it backwards. You're starting with the smallest problems and then you build upwards. And for a dynamic program to be suitable, there are 2 properties needed. We still have this optimal substructures problem, so that the optimal solution contains the optimal solutions to subproblems, and that's why we can break it down to smaller problems. And then we have overlapping subproblems. And that means that the same subproblem is included many, many, many times. I mean, this 3 plus n example is one example where if you compute, I mean, the same number is included in multiple sequences. So, and that is the key here, that we only need to compute each subproblem once, and that's the whole point. So by doing that, we can get a much higher efficiency. And then there's this top-down, where you basically have this table with the previous solutions. You check, is my solution in the table? Yes, fine, return it, otherwise compute it. And then you have bottom-up, where you start from the smallest problem and build upwards. Sometimes you also need to display the solution. Then you need to remember where you came from. And this can be done as well. So there are many different DP problems. For example, finding the maximum one-dimensional sum. So basically the maximum subsequence in a sequence with the maximum sum. You can do that in array. So you basically the maximum subarray, longest increasing subsequences, knapsack, coin change, traveling salesman, person, and so on. And below we have just what are the states and how do you compute the kind of transitions and what the time complexity of that is. So we will talk much more about the DP problems probably already tomorrow. There is also a large variety of data structures. So a general advice is learn the basic data structures and learn to use them efficiently, the ones that are built into your favorite language, like vectors and stacks and queues and priority queues and so on. And of course, graphs that you need to do yourself, strings and so on. This is just a long list of things that we will be going through or using in this course. There will also be some mathematics. I think we will talk about this later because the time is up. Programming languages I have talked about. My general advice there is get to learn to use your programming language efficiently. You will save a lot of time. It's probably a good idea to have some templates to simplify your implementations. And testing and debugging is extremely important, so learn to do that efficiently. So today I've introduced the course and I've introduced you all to algorithmic problem solving and some kind of general approaches to address problem solving. Tomorrow and on Thursday, there will be more hands-on discussion around concrete problems. And yes, I will upload the slides after this lecture. So with that, thank you very much for today. And hopefully I will potentially see some of you tomorrow. I'm not sure if I will be one of the people on site or not, but I look forward to hopefully seeing you in person as well. So there is the question about this language, and I realized that I said there was only a few languages. I will double check and get back. I'm a little bit uncertain what we have said before, but normally I would say that all languages that Kattis accept, we would accept. But I will provide a clarification. Could you repeat what the purpose of the lab session on Thursday is? So the purpose of the lab session on Thursday is to practice problem solving, so that actually implementing these solutions and getting them to work. So there will be a problem set and we will go through the problem set tomorrow so that you will try to solve them kind of on pen and paper, and then we will discuss them. And then on Thursday, you will implement and try to get these solutions to work for real. So it's a practice of problem solving. Okay, thank you very much and have a nice day.